Hello, wonderful Earth Science kids. Today we're going to be looking at reading synoptic weather maps. Now, what is a synoptic weather map? Oh, that word synoptic certainly sounds tough, but it comes from the word synopsis. And if you think of what a synopsis is, it's an abbreviation. If you have to write a synopsis of a chapter in a book, you're writing a short summary of what occurred in that chapter. So a synoptic weather map is a map that shows a variety of weather conditions, all in one weather map in such abbreviated fashion that you can see over a huge weather map all the different weather variables on a large region. So information on that synopsis, that abbreviation, might be shown about temperature, pressure, precipitation, winds, and other weather variables. Because weather moves across the United States from west to east, a synoptic weather map, you're seeing what the weather is like across the country right now. You can make predictions on what the weather is going to be in different places in the future. So to read station models, station model is that synopsis. It shows a variety of weather variables in a very small space. Station model contains an abbreviation of all the weather data. So this station model describes what you will find on page 13 in your reference tables. So here's the station map symbols that you'd find. Everything is on this page, all put together, really nice and neat. Everything you need here is described for you. The temperature right here, notice it's 28. It doesn't say degrees Fahrenheit, but it is degrees Fahrenheit. If you're reconstituting this and they tell you to put information on the station model, notice they don't have degrees Fahrenheit here. Don't you put degrees Fahrenheit there. You put it on the way it is shown here. The only part that might be a little challenging to understand is how we're going to do barometric pressure, and we'll describe that as we go on. So very straightforward to understand. Just look at this on page 13 in your reference tables, and you will understand how all this works. So the circle shows the location of the station, right? It's right over the city where the data was taken. The first thing is the amount of cloud cover, and that's shown by how much the circle is filled in, and it's always in quarters. If it's 15% cloud cover, they would say it's 25%. You go to the nearest 25%. So 0, 25%, 50%, 75%, 100%. And if it's not quite that, and when would it ever really be that, nobody really cares. You just make it as close as possible. The line coming out of the circle shows the direction the wind is coming from. Nobody cares where the wind is going to after it leaves the station. They want to know where the wind is coming from, because that's going to allow you to predict the weather, because the weather is coming from where the wind is coming from. So the feathers indicate wind speed, and each are worth 10 miles an hour. Half feathers are worth 5. And now that's really in knots, which is nautical miles per hour. Nobody's worried about it. Just call it miles per hour, and you are fine. So what is the amount of cloud cover in this? Well, we see the cloud, the station model is completely filled in, so it looks to me like 100%, and it is 100%. What is the wind direction? Well, the wind direction looks both a combination of south and west. How about southwest? Sounds good. And what is the wind speed? Well, I see a whole feather and a half feather. So that's 10 miles an hour and 5 miles an hour, 15 miles an hour. The air temperature in degrees Fahrenheit. This is the US, and we use Fahrenheit. So the air temperature in degrees Fahrenheit is the number at the top left. The dew point is shown on the bottom left. Now, these two numbers are the really important numbers here. Dew point is really an indication of how much moisture is in the air. That's important because that's going to show you basically how explosive this air can be if you lift it up. How much heat is going to be released as you condense? Well, that's an important number. Anytime the dew point gets above, say, 70 degrees Fahrenheit, that air is very explosive. So dew point and temperature are really important numbers. They are usually always shown on the weather map. If there's a symbol on the left side of the station model, it shows what the present weather is. The number to the left of that symbol shows the visibility. And very often that's not there unless it's an important visibility, like a lack of visibility. So these are the symbols for the present weather. Notice rain would be a dot. Thunderstorms would be this neat symbol here. Snow right here. But is there anything to memorize? No, this is on your reference tables. It's right by that station model diagram. So everything you need is at your fingertips. When you see a symbol there and they want to know what the present weather is, there it is. It's right there. So let's try this. What's the temperature? Well, I see 65 right on top. Right here, you see 65. So 65. And you also see, what's that going to be? Dew point. Good. What's that number going to be? That's your visibility. So that would be 3 miles visibility. And you got to refer back. What is that thing? All right, well, let's go through it. So the temperature is 65. What's the dew point? 43 degrees Fahrenheit. And notice, don't say 65. There's Celsius scale, Kelvin scale, and Fahrenheit scale. We're on Fahrenheit, so say 65 degrees Fahrenheit. 43 degrees Fahrenheit for the dew point. What is the weather? Well, the present weather, that dot, you look on it. What does it say? Rain. So it's rain. What's the visibility? 3 miles. Okay. What is the cloud cover? Oh, I'm sorry. What's the wind direction and speed? Well, the wind direction looks like it is both a combination of north and east. And that feather, it doesn't look that big. So I'm saying northeast at 5 miles an hour. How about that? And then what is the amount of cloud cover? 25% filled in, so it's 25% cloud cover. These are pretty easy to read. Now, if there's any challenge here, this is it. To the top right is a 3-digit code showing the pressure. To decode, add a 9 if the number is greater than 500, or a 10 if it's less than 500 in front, and place a decimal before the last number. The number to the right shows the change in air pressure over the last 3 hours. A decimal must be added between the numbers. So let's talk about this number for a second. Why are we doing the things we do? Well, first of all, there is a decimal between the 9 and the 3. Always. Just before the last number, there's a decimal. So this number is something 09. So would that be 909 millibars or 1,009 millibars? Did you add a 9 in front or a 10 in front? Well, just ask yourself. The average pressure on the Earth's surface is about 1,000 millibars. It rarely ever gets below 950 millibars, and it almost never gets above 1,050 millibars. So which number, a 9 or a 10 in front with a decimal at the end, would get you closest to 1,000? Clearly, if you say a 9 in front, that's 909.3 millibars. No, that can't be correct. This would be in the middle of a devastating hurricane if that were the case. So this is not a hurricane. So 1,009.3 millibars sounds good. And how much has the pressure gone down? Well, we put a decimal between these two numbers, so it's 2.1 millibars, and the minus indicates it has gone down. So I think we got this. So what is the pressure? Give you a second again. Excellent. 1,009.3 millibars. Don't forget to put the millibars at the end. It would never show up on the station model because that would be unnecessary writing, which we shun on any station model. Otherwise, we'll fill a map with so much writing. So we reduce the amount of writing as much as we can. So the millibars are implied, but if somebody asks you to reconstitute it, make sure you put the millibars there. What is the change in pressure over the last 3 hours? It is decreased by 2.1 millibars. Hey, what's the wind direction and speed? I see from the west at 10 miles an hour. What's the cloud cover? 0%. Now, what is the air pressure? 878. Well, we put a decimal before the last number, so it's something 87.8 millibars. Would that be 987.8 millibars or 1,087.8 millibars? Clearly, the 987.8 millibars is closer to 1,000. 1,087 millibars, that really never gets that high on Earth. So we're talking 987.8 millibars. And what has been the change in air pressure over the last 3 hours? Well, it's increased 1.5 millibars. Okay, so is the weather getting nicer or less rainy and more clear and whatnot? Well, you can tell without cloud cover, it's probably clear anyway. But is the weather going to stay that way? Well, the air pressure is increasing. That suggests that the air is getting more clear, more pleasant, if you could call it that. If the air pressure was decreasing, it could be heading for storms, or a storm that you have could be getting worse. So the number to the lower right is the amount of precipitation in the last 6 hours. Not all information is going to be given on all station models. As a matter of fact, it's rare that all information is given on station models, but if it's given, it will always, always be in the form described here on your reference tables. How much precipitation has fallen in the last 6 hours? I see 0.35. This is the United States. We use inches, so 0.35 inches in the last 6 hours. What's the wind direction and speed? Well, we're still seeing west at 10 miles an hour. All right, and what is the air pressure? 010. Put a decimal, so it's something 01.0. Would that be 901.0 millibars or 1,001.0 millibars? Which is closer to 1,000? I'm thinking the 1,001.0 millibars would be it. What's been the air pressure change? 0.3 millibar increase in the last 3 hours. Okay? Now we move on to air masses. An air mass is a large area of air that has the same temperature, pressure, and humidity throughout. We assume the pressure. The thing about an air mass that's important is the temperature and humidity. Because the movement of air masses is what's going to bring us changes in weather. The leading edge of a new air mass that's intruding onto your area is called a front. Precipitation is often found right on the front. So after an air mass passes, now you're within the new air mass and the weather usually clears. You're not having precipitation anymore. So what front is coming to you is of utmost importance in predicting your weather. So air masses are categorized really by their temperature and their humidity. So for an example, if an air mass originates from Canada, northern Canada, well, what's northern Canada like? Well, I think you'd realize it's cold and dry. So if you have an air mass from that region, it's going to also be cold and dry. How about an air mass from the Gulf of Mexico? Well, warm and moist, it's certainly going to be the conditions in the Gulf of Mexico. So the air mass would be warm and moist. So this is pretty easy. The other understanding that you have to have is from Canada, cold and dry, that is high pressure. By definition, that's high pressure. That air is sinking. It's heavier because it's cold. It's also heavier because it's dry. So sinking gives you high pressure. Warm and moist. Warm makes air rise. Moist also makes air lighter. So that air is going to be rising, giving you low pressure. These are where our air masses come from. If you look at the world wind circulation diagram, you'll see in the middle of the U.S., it's windy. Air masses don't sit over here. But at 30 degrees north and at 60 degrees north, you can have air masses just sit in a spot. So here you can have an air mass sit for, say, a week, and that's going to turn into whatever the area underneath it is. So continental polar. Continental means dry. Polar means cold. So cold, dry air coming from northern Canada. Continental dry, tropical hot. So hot, dry air coming down from the desert United States. Maritime tropical. Maritime refers to oceans. Tropical is warm. So warm, moist air coming from the Gulf of Mexico. Warm, moist air coming from the southern Atlantic Ocean. Cold, moist air coming from the northern Atlantic Ocean. So these would be the air masses that we get. Arctic is something we would get rarely because the Arctic has to pass through places that would warm it up before it gets to us. So generally we have the 4 different air masses, continental polar or maritime polar being the cold air masses, continental being the dry one, maritime being the moist one, continental tropical or maritime tropical being the warm air masses, so we can have a moist warm or a dry warm air mass. So we use these following codes. Notice the first letters are always lowercase. That's important. So it could be continental or maritime, referring to dry or humid. The second letter is always capitalized, polar or tropical. So we combine CP, continental polar, cold and dry, CT, warm and dry, MP, cold and moist, and MT, warm and moist. So this is just a weather map showing some fun we had some years ago. Notice there is a low pressure here. There's a frontal thing happening here. That low pressure gets off the coast. We're going to start studying how these lows form these amazing storm systems. So we have an air mass coming down from northern Canada, making this blue with spikies on it. This is a cold air mass. This is then the warm air mass, or the warm front. This warm air is moving this way. This cold air is moving this way. The low pressure is in the middle of them. Condensation is forming, releasing huge amounts of heat, deepening the low. Watch what happens. That low becomes more defined here. Precipitation starts in a little bit. As the low moves up the coast, this warm front is pushing this way, cold front pushing this way. Clearly, it is making a heap of snow over New York State here, making a nice day off of school over here in New York State. This is a classic low off the east coast of the United States, moving up to the north. And this is a nor'easter because air wraps around this low counterclockwise. So for us, the air is coming from the north and east, an unusual direction. So when we have air coming this way from the north and east, that is usually associated with those big bad storms. Hey, thanks for watching.